So, the future of API specification is static analysis. That's the thesis that I'm going to defend. So, just to be very clear, the Parus Integration Excellence Center doesn't promote specific ideas specifically. It's more like an arena. So, I am the one claiming this, not the Parus Integration Center, not Sinetiq. So, if my arguments are bad, please tell me, because this is meant to be like a live discussion, okay? So I'm going to argue for a particular case, and then you can counter-argue if you want to, or present a different case, and so on. So this is more like a forum or an arena, okay? So let's see what we can learn. Okay, who am I exactly? Well, you saw the picture. You can see me. I'm here. I'm a consultant at Sinetiq, currently working mostly with development and system architecture. I work a lot with APIs. And this is one of the reasons why I felt this is so pertinent, API specification and making it better, essentially. I care a lot about developer productivity, and I think it's very frustrating to work when you're not productive. So productive is fun, and I want work to be more engaging and interesting. So I'm going to discuss 4 different points today. What is static analysis? How does static analysis help us? So first, what it is more like at a fundamental level, kind of. Then secondly, how exactly does it help us? Not like why is it useful, but more like what is the philosophical picture it fits into? Like what's the big deal? And you will see that there are a lot of other things that fit into this picture too, not just static analysis. And then thirdly, how much can static analysis help us? What are the boundaries? Like what determines how useful a particular static analysis tool is? And then fourthly, how do we make current tools more useful? And implied in that is, I'm claiming that the current tools aren't very useful and that they could be a lot more useful. And I'm also going to cover why they aren't more useful than they are. All right. So what is static analysis? Well, it's feedback before going live. That's like the easy explanation. Typically right in your editor. So if you've been typing an email at some point and you misspell the word, then maybe you've seen these squiggly lines appearing below the word. That's a form of static analysis. The email client that you're using has some kind of vocabulary or some kind of glossary that you can use to look up all your words. And if it notices something it doesn't recognize, it will highlight it. Typically, you can get the same kind of thing for grammatical errors, but then it needs to know what language you're writing in. Of course, it needs to do that for the words too. And then it's able to highlight the parts of your document that is incorrect or could use some improvement. If you've been doing computer programming, you will recognize those squiggly lines too. They typically appear all over the place in most editors today. You have linters and language servers and different kinds of static analysis tools that tell you that, hey, you're referring to a variable that is not defined, or hey, this class doesn't seem to exist, or hey, you're violating this invariant, or whatever it is. So it's a very important tool for getting immediate feedback. You may wonder where the term static analysis comes from, and that's a programming language term, really. The word static refers to the time before the code is executed, so like while it's written or before it's compiled into a program. So sometimes the word static is used synonymously with compile time, so while you're compiling or like before running. So maybe like design time analysis would be like a better word, the more general term. But this is the term that people recognize more than any other, so that's why I'm sticking to it. But then maybe we should call it design time analysis or something like that as we go ahead. All right, so static analysis, design time analysis, help, feedback, squiggly lines. How does static analysis really help us? Well, of course, it makes you able to have less spelling mistakes in your emails, or less programming mistakes in your program. Sure, we all understand that, but what's the big picture? I'm arguing that there's something called the design feedback loop, and it generally goes like this. You start off your project at some point, and during this start, you're going to decide on a goal. You're going to elect people who are going to be part of the project. There's going to be a chain of command, like what are the developers, who is going to be an integrator or an architect, and so on. And then you're going to produce some requirements. And after that, you're going to have to design your system, you're going to have to implement your system, and you're going to have to integrate your system into a larger environment. And then after that, you're going to have a party, and you're going to thank everyone for being great and for not messing up entirely, and then the project is over. Something like that. However, at each of these steps, you might discover that there's a fault or problem that was produced in a previous step. And then you have to go back, and you have to fix it there, and then that fix is going to trickle down on all the things that you've already done, and you're going to have to change things further down. So if we take an example, let's say that we are designing a building, and we're writing pillars that a lot of floors are going to rest upon, and then while we're building the building, we notice that, oh no, this pillar, it's not going to hold 30 floors or 40 floors that we're going to put on top of it. But we have 30 floors on it already. So we're going to need to move it or make it thicker. That's a problem. It's going to cost a lot of money. But if you notice that problem right here, you only need to move a couple of pixels in your CAD tool, and then you're done. So you want to detect issues as early as you can. That's really the gist of this picture, that the sooner you can loop back, the more time and money you save. So you want to detect things as early as you possibly can. If we move on to this picture, actually you can break up each of these 3 steps. You can break up into 3 other steps. So each of these particular steps is going to have sub-steps. And the first one is exploration. So before you start designing, for example, you need to know what your constraints are. So what other systems exist? So let's say that we are designing a brake chip for a car or a truck or something. So we have a project group. We know that the chip can be about this big. It needs to fit somewhere in the car in particular. We know that we have some kind of requirements. We need to fire the brake if something happens, if a warning is raised or whatever. But then we need to know, what does the rest of the car look like? Where do we fit in? So that's the exploration phase. And sometimes you notice that, okay, yeah, we don't really fit in. There's a problem. Then you have to go back to the requirements and start to change the requirements, or you won't be able to finish your job. After exploration, you actually produce the thing. Then maybe you notice that, oh yeah, the chip that we chose, it has too little RAM. We can't do all the functions that we need to do with this amount of RAM. We need a bigger chip. So we need to go back to the requirements and ask for being able to use a more expensive chip. And then in the test and verification stage, what you do is that you test first off that your thesis, your idea of what the artifact is supposed to do, holds. And then after that, or as part of doing that, then you check whether or not the artifact you produced actually satisfies the requirements produced for it. So 2 different steps that I baked into one here. And of course, if you detect something that is wrong, then you have to go back. Either you have to go back to producing the thing, or you have to go back to figuring out something you didn't know about the environment and how you're supposed to fit into it. Or you have to go back to the requirements or an earlier phase or whatever. And this repeats again for implementation and integration. So in the integration stage, for example, we already mentioned that you have to fit physically into the car. Maybe you don't actually get enough power from the power cord or whatever. That's a problem that needs to be fixed, and you might need to backtrack. So, and obviously in all of these different steps, different professionals and different tools will typically be active. So here you will have something like architects, developers, and system integrators. And then in the exploration phase, then you need to do experiments. You need to read documentation. You need to interact with the kind of environment and thing that you're interested in. Production, then you have development environments, or you have a tool for writing architecture documents and so on. And then testing, maybe you have unit test tools, integration test, quality assurance. You can have all kinds of different processes associated with these steps. So the point of using static analysis is to loop back earlier so we can save time and money. Essentially, we want to be productive, we want to have high quality output, and we don't want to waste time. That's it. So static analysis is one little part of this. It's not like a huge part, it's one part of it, and it can help. You also need to have things like reviews. You need to have an efficient structure, organization-wise, and so on. Right person needs to be accountable. There needs to be accounting, and so on and so forth. But that's the big picture. So how much can static analysis really help us? What are the boundaries for the limits, essentially, for what static analysis can help us with? Well, it depends on how much context we give it. So context, that's a big word. I'm going to claim that when it comes to static analysis, context is king, actually. We'll get back to that. So what's this? This is a computer program, and this is the, I don't know, like the original context for static analysis tools. So we're defining some variable x, we're setting it to 5, we're squaring it, so it becomes, the y over there becomes 25, and then we're adding it to w and then calling some send function. Is this a correct program? So let's pretend we're a static analysis tool and we're going to go through all these expressions and we're going to provide feedback. I already spoiled it, okay? There are already red squiggly lines over there. But the thing is, though, that with the information I've given you up until this point, we don't know enough to know if this is the correct program. We need to know what programming language it is. What's the specification language? And if I tell you that it's JavaScript, then you can know that math.pow is actually part of the standard library. And it accepts 2 arguments and returns the square, or the power of. So in this particular case, the square of x. And if I tell you this is the entire program, there are no other program statements, then you can know that w is not defined and that send is not defined. And obviously that's a problem. So this is not a correct program. But if I tell you that this is a manual script, and in a manual script, then send is always defined to be a function that sends me a text message, and that w is always defined to be 10 million, then I would get a text message with 10,000,025 in it. And then it would be a correct program. So we need to know the specification language, essentially. And then also, we need to know of a program in that language or some kind of specification in that language. And obviously, this is the same case for API design. So if you're designing an API, then maybe you do it in OpenAPI, Async API. Maybe you have some Web IDL or SOAP specification. There are tons of specifications that have been coming over the years. Apache Avro, Thrift, and so on. So you have some kind of language, and you specify your API in that language. And given your specification and the language specification, a static analysis tool, like a language server or a linter, can go through your program and detect issues. If you remove any of those two, then you have nothing. You can't have you can't detect any issues. So the more context is available to the static analysis tool, the more analysis it can perform. But, oh yeah, let's move to the next slide. So this is really like the million-dollar point here. We need more context to perform more analysis. Oh yeah. Yes. How do we make current tools more useful? And then implicitly, why aren't they more useful than they are? Or could we? What's the gap, essentially? So this is Visual Studio Code. I don't know if you've used it. It's one of the most popular editors right now, especially in web development. So if you have like user experience people or UI people at your company, this is probably the environment that they use. And what I'm writing here is an API specification for Donut Dispenser 9000. I started writing the specification, and you can't see it here, but I'm writing an endpoint, an operation. And I misspelled, or I wrote operations ID here. It should be operation ID without the S. And the linter that I've installed noticed this, and it says that property operations ID is not allowed. Essentially, what I've done is that I've broken the language specification. The language specification for OpenAPI stipulates that every path has to have a field called operation ID. And there's and together with a number of other properties that you're allowed to use. And operations ID is not in that list. So, and this is fairly typical. Like, this is one of the kinds of things that we can expect current static analysis tools to help us with, which is to say that if we violate the language specification in our program, in our code, in our specification, those are the kinds of things. So like if I would refer to another OpenAPI document or to a JSON schema document through a link, and the link is wrong, then the tool will also tell me. But if I do something else, like if I change my API after, let us say that I finish the API, it's implemented in some kind of system, and then later on I go back to the API and I make a change that is a breaking. So if someone would use, if someone developed a system to use the old version of the API, but then change to a system that uses the new API, then it won't work anymore because it's a break and change. But then let's say while I did that break and change, I forgot to change the version number. So now you're going to get a mess in production because you're not going to be able to determine reliably what components to match to each other, and things are going to explode in production. And this tool, I can promise you, is not going to help you with that. So it's not going to tell you, hey, you did a breaking change, you need to change the version number, because it doesn't know that. The tool have no idea what you have put into production. It has no idea which versions of this document have been released somewhere. So the version number to this tool is completely it's just a string, it doesn't really know. The only thing it can tell you about is whether or not the version number is well formed. Does it contain 3 digits or not? So if you write happy birthday in version, it's going to complain. But that's about it. So that's the limit. So they are not more useful than they are because we're missing some really important contexts. Context is king, okay? So ideal, interface definition language. In our case, in the last example, or in the last slide, it was OpenAPI. And then we have the actual API that I wrote, Donut Dispenser 9000. Those are the 2 things that we have in our current static analysis tools. That's the only context they act upon. And the reason, of course, is because static analysis comes from the programming language community. And what do you have? Let's say you have this huge Java program that you've written. Then the IDL in that case, or the language, would be Java. And then the huge library you've written would be the equivalent to the APIs there. So that would be the specification. And what else do you have? What else is relevant to analyze, really? Not really much. You can come a really long way and do a lot of different analysis just looking at Java and Java code. But when you come to API specification, it becomes more complicated because APIs, they don't really live in isolation, but we treat them as if they do. We develop them as if they're islands in and of themselves, not connected to anything else. And because of this, we don't really get that much context, and we can't make that many useful analysis. So here are 4 proposals of things we could add to the context traditionally used. Profile, that's one thing. So let's say that you have a policy that you always use encrypted protocols. And so if you specify in your OpenAPI specification that access to this particular protocol is through HTTP rather than HTTPS, then you would like to have a warning. So if you have some kind of profile somewhere that states in a machine-readable way that every single operation has to be an HTTPS operation, then you can get an error. While the designer is typing in the operation into Visual Studio Code, you could get a little red squiggle line saying that, hey, you need to use HTTPS. And if you use HTTPS, you have to specify trusted certificate authorities and so on and so forth. So profiles is something you can use to enforce your own way of using the specification. I don't know if you've ever been in a project where where they develop C++ or Java or whatever, but a lot of companies, they have these huge documents that you as a programmer are expected to read before you actually touch the code. And in it, they will have guidelines on how to name functions and how many classes to write and whether or not you should follow the solid principles and so on and so forth. And you have to dig through this, and then afterwards you're allowed to maybe touch the code. And if you violate anything in this profile, handwritten profile, then during review, code review, then there will be tons of angry people yelling at you and throwing shoes at you for not paying attention to page 14 in the guideline and missing this particular thing over there, which they happen to care a lot about. And what I'm saying is that, well, if you have a machine-readable profile, you don't need to write that document. You can have the editor showing you red squiggly lines instead of throwing shoes at each other, which is a lot more efficient and a lot more discreet, and people won't fight as much. Another one is history. So almost every programmer today uses Git, which is a version control system. And similar things are used in a lot of other contexts too, much because of the enormous success of Git. So what we have is in our Word documents, in our emails and whatever, we have a complete history of all the changes. So if we have a history of all the changes to an API, for example, and we can know exactly at which points in this history the API was released, then we can know if a breaking change breaks a commitment to an earlier version. So the version number thing that I told you about earlier. So if we allow the static analysis tool to also capture the history, then we can help you with setting a correct version number. You don't have to do it yourself, essentially. That would be a great help. Third one, connections. As I told you before, APIs, they never live in isolation. It happens, like if you're Facebook and you're making like a public API for anyone to consume, then maybe you don't know who will actually consume your API. But if you're like at a car manufacturing company and you're developing a brake component, then you know exactly who's going to be talking to your API. Those other 7 components. And that's it. So what if you just specify that? Specify that in a machine-readable format and make it available to the static analysis tool. Because if you do, then suddenly the static analysis tool can notice if someone is not using one of your operations. So yeah, this thing is waste. Why are you spending time on improving it and fixing it? Because no one is using it. Or let's say that you're putting in your web service in your cluster and you want it to run, and if you have a specification over what other services it needs to function, you can tell right away if they are there or not. And if they're not there, you can get a warning. Hey, if you put this into production now, it's just going to spam your logs with tons of errors because not all the other components it depends on are present. And this is a pretty big deal to us to us at Sinetiq, because we have been thinking a lot about the connection thing. But there are more. Last one, executables. So if you have all this information, for example, let's say that we have an open API specification, it's written, and it has tons of information in it, and maybe you have profiles and so on. And then while we are programming, so while we're writing the programming code, then the editor that we're using to write the code is aware of these things. So if we, for example, violate like a quality of service guarantee that we promised in the profile. Let's say that we want all services to respond within 500 milliseconds or whatever. And then while you're developing the executable, you're inserting a sleep statement. Or you're telling like, hey, when you see this thing, do nothing for 2 seconds. So if the editor was aware of this profile for the API, then it could just tell you right away that, hey, you're violating the specification now. You're not allowed to sleep for 2 seconds. So it's really about like interconnecting all these things, like making as much information available in as much places as possible, because then you can use that for analysis, and you can use that to detect errors quickly so that you can tighten the feedback loop. Here's an example of what an API specification interconnection specification might look like. That was a mouthful. So this is again the donut dispenser 9000, and we're just telling here that we're consuming some kind of payments API, because you're going to have to pay the donuts dispenser or it won't give you any donuts. And then we have a dough ordering system. So let's say that the donut dispenser has some kind of internal oven, but you need to fill it with dough every now and again, or it won't be able to spit out new donuts. And then it provides another API, donut ordering, which might be implemented or used by like the little machine that sits on top of the dispenser that people use with their credit card to pay. So now we have a specification of like the inputs and outputs essentially. What kinds of APIs are being used by the donut dispenser? And now we can use this to determine, are all the APIs it needs or consumes, are they present? Is there anyone using the service it provides? Because if no one is, then the whole thing is useless essentially in your cluster. You don't need to deploy it. Yes, and obviously you could add a lot more information to this. You could add like version numbers and so on, so you can tell that when you redeploy or when you release a new version of a component, you can determine right away if it will work or if you will break compatibility with some other service in that cluster and so on. So that enables like a new world of analysis. Okay. So static analysis helps us tighten the feedback loop, but we need to give it more context if we want even tighter feedback loops. And now what? So hopefully I convinced you that static analysis is a great idea. The best would be if I had some kind of magic tool I could just pop out of my pocket and tell you, hey, use this, and it solves all your problems. But that's not the case. Right now, we need to help the industry tighten the design feedback loop. That's the next thing. I don't have any tools that do this. I don't know of any tool that does all these things. Every single tool I've ever looked at is stuck in the IDL/API. Like if you go back to this picture, they're all stuck in those two. None of them is extending further, even though they could. Because I don't think this is an idea that has taken hold really in the industry yet. This is not something that people don't really, at least not generally, understand could be a good idea. And this is the reason why I thought this would be a good talk. So be on the lookout for and promote great tools. Like if someone does something that does this, now you know it's a good idea. Promote it. Try to make people use it. Tell us about it. And if you have the resources, like a lot of companies, especially bigger ones, that design some of their own tools internally, well, why not make your own? And if it's successful internally, try to publish it as open source and try to use it to boost your own credibility in the industry so you can attract talent and so on. Or maybe join us and help us find the best way to produce quality designs quickly using all possible kinds of tools. And not just tools, also processes. Like how do you produce efficient designs or component-based designs quickly and correctly? That's like why Parus Integration Excellence Center exists, essentially. All right, so I finished a few minutes early, which means that we have even more time for questions.